Welcome back to my channel. I'm Dr. Dorcas Ngigi. Today we're going to look at a new topic, a new subtopic, the apparent loss in weight. Okay, so we're going to look at apparent loss in weight. So in the previous lesson, the lesson we did last, we looked at upthrust. And we said that upthrust force is a force that is exerted by fluids on objects that are placed inside the fluid. Okay? We also said that a fluid is a term we use to stand for both liquids and gases. We worked out and we saw that we were able to derive that upthrust is equal to the weight of the fluid displaced by that object which is inside the fluid. We said upthrust is equal to the weight of the fluid displaced by object that is inside the fluid. Now today we are going to look at another way to determine upthrust, and that way is the apparent loss in weight. Okay, so welcome. Let's go together. Now let's take an example. If you have an object that is hanging freely in air, an object that is hanging freely in air. Now this object hanging freely in air is experiencing an upthrust due to air. Okay, because air is a gas, so it has its own upthrust. So this object, which is hanging freely in air, is experiencing an upthrust by the air. But the upthrust due to air is very small. The upthrust due to air is very small. Why? Because the density of air is very small, 1.25 kilogram per cubic meter. So that's very small density. So the upthrust is very small. So we are going to take the weight when an object is hanging in air to stand for the true weight of the object. We're going to get the weight when an object is hanging in air to be the true weight of that object. Because we have said the upthrust due to air is very small, because air has very low density. Now, if we take that to be the true weight of the object, and let's say I'm using a spring balance. Let's say I'm using a spring balance. Then whatever my spring balance will measure, I'll take it to be the actual weight of my object. And I've said because the upthrust due to air is very small. It does not mean that it's not there. It is there, but it's very small. Okay? Now, if I take the same object, and this time I immerse it totally in a liquid, I immerse it completely in a liquid. Now my spring balance will not read the same thing, because the upthrust this object is experiencing in air is different from the upthrust the same object will experience in a liquid, because a liquid has a larger upthrust. So whatever the spring balance is reading, it's reading the resultant force. And this resultant force, remember, it is the weight mg, the acting downwards, remember the last lesson, minus the upward force, the upthrust. So whatever my spring balance is reading will be the resultant force. So in the first case, I'm reading the actual weight because the upthrust is very small. But in the second case, I am reading a force, the force my spring balance will be reading is not the actual weight, because there is upthrust. So it is reading weight minus upthrust. So I'm going to call that reading, that force, apparent weight. So I take in the first case, I take that to be the actual weight, W. And then in my second case, I call it the apparent weight. Which is, I call it A. Okay? So A is the weight I'm going to read. When an object is inside the liquid, and it is the reading, is the weight, the force, my spring balance is, we read when that object is totally immersed, and is a resultant force. There's the weight downwards, and there's the upthrust upwards. Okay? So if I take the weight, because the weight is always greater than the apparent weight, then what exactly do I get from that? If I take the weight, I subtract the apparent weight, then what do I get? What I get is upthrust. Let's see why. This is the actual weight. We are assuming the upthrust is negligible. Let's say we are assuming is 0. Now, in our second case, the upthrust is not 0. So the reading we are getting here, the apparent weight, is a resultant force. It is the weight downwards minus the upthrust upwards. So if I get the weight, actual weight, minus the apparent weight read by the second spring balance, then what I get is the upthrust. Now that upthrust, U, which is weight minus apparent weight, that upthrust is what we are referring to, the apparent loss in weight. That is the weight we have lost when we move an object from air into a fluid. When we move an object from air and totally immerse it in a fluid, then what we get, the force, the weight we feel is less than the weight we feel when that object is hanging in air. That loss is what we are calling U, is the apparent loss in weight. So our upthrust is the apparent loss in weight. Upthrust is also called the apparent loss in weight. Okay? So today we are able to see, we have seen that upthrust can be calculated in a very simple experiment. Upthrust due to any fluid, mostly liquids, is very easy to determine it in a laboratory setting. All you need is a spring balance and your object. Get the weight of the object when it is hanging freely in air. Record that as the weight, actual weight of the object. Then take the fluid, liquid whose upthrust you want to determine. Then let the object be totally immersed in that fluid or liquid, and let read the apparent weight. Read the apparent weight. Then the upthrust due to that liquid will be given by the weight minus the apparent weight. And that is the upthrust due to a given liquid on a given object. Okay? Now, if life cases, if you were to hold a jerrycan of water and hold it, lift it in air, and then take the same jerrycan of water into like a river and lift it when it is totally immersed in water, then you realize that it is very easy to lift that jerrycan when it is totally immersed in water than to lift it when it is in air. Now we understand why. It is because in water, when it is totally immersed in water, there is an upward force which is helping you lift the jerrycan. That upward force is our upthrust, and it is the apparent loss in weight. Okay? Now we need to look at an example. So let's say we have a ball of radius 7 centimeters, is immersed in water of density is mass in water of density 1000 kilograms per cubic meter. We have a ball of radius 7 centimeter is massed in water of density 1000 kilograms per cubic meter. Okay. Now determine the upthrust on the ball determine the upthrust on the ball. Okay. Now the first question we are going to ask ourselves, what is upthrust? Now from the first thing, we saw that upthrust is equal to the weight of the fluid displaced. That is number one. Okay. The second thing we saw that the volume of the displaced fluid, which in our case is water, must be equal to the volume of the object which is totally immersed in the fluid. So assuming our ball is totally immersed in our fluid, then the volume of water it is going to displace should be equal to its own volume. So volume of ball equals to volume of water displaced. Okay, so volume of ball equals to, now is a ball, let's say a ball is spherical, so that is 4/3 times r cubed, so there's 7 centimeter times 7 centimeter times 7 centimeters. Okay. Now with this we get the volume of the ball, which is also equal to the volume of the displaced fluid. Now from this one, then the question is, what is the mass of the displaced fluid? Now to get the mass of the displaced fluid, I need the density of water and the volume of the water. So this volume is also equal to volume of water displaced. If I take that volume, I multiply that with my density of water, so times 1000. Now let's convert this mass. Okay, let's use kilograms. Now for that, I need to divide this by 1 million. Why? Because I want to change centimeters cubic to meters cubic. Remember, 1 meter is 100 centimeters. So 100 times 100 times 100 is 1 meters cubed. So if I divide this by 1 million, then I'll have gotten my volume in meters cubed. Okay, now I have mass, then I need to multiply that mass, which is now in kilogram. Remember, centimeter, centimeter, centimeter. Now by dividing by a million, I have now the answer in meters cubed. So that's 777. So of course the per cubic meter will cancel with meters cubed. Remember, if you have a raised power m multiplied by a raised power n, that is the same as a raised power n plus m plus n. If you have a raised power m divided by a raised power n, that's the same as a raised power m minus n. Okay. So here, the base is the same, meter. So 3 plus minus 3, that is 0. Any number raised to power 0, that is 1. So this gives me the mass, this density times volume. Density times volume gives me mass in kilogram. Now we want to get weight of the water that is displaced. So I must multiply this by gravity. What is gravity? Is 10 newtons per kilogram. Okay. Now we have kilogram and per kilogram. So what do we get? Whatever we get will be in newtons. So there is 1, 2, 3, 4. 1, 2, 3, 4. So this is around, so we can say upthrust is 4 over 3 times 7, that's 49 times 7. This we have cancelled, so all of that are newtons. That becomes the upthrust. So you only need to work out that 4 multiplied by 49 multiplied by 7 over 3. That becomes the upthrust. So it's very easy. What you need to notice is, 1, the volume of the ball is equal to the volume of the water that is displaced. That's number 1. Number 2, that volume of displaced water times the density of water gives you the mass of the water displaced. Remember, we're using the volume of water displaced. So volume of water displaced times density of water gives you mass of water displaced. We're almost there. So the mass of water displaced times gravity G, 10 newtons per kilogram, gives you weight of the water displaced. And what is the weight of the water displaced? Weight of the water displaced is upthrust. So they determine the upthrust on the ball. So the upthrust of the ball is 4 over 3 times 49 times 7 newtons. So today we have looked at the apparent loss in weight. So thank you for watching. I hope to see you in my next video. Don't forget to subscribe and to like. Thank you. Till we meet again. Bye.